So recall that we're looking at a Sturm-Liouville problem of this type. So we've got our Sturm-Liouville operator over here and our eigenvalue lambda. We're doing this on some domain. And we've got these what are called separated boundary conditions. So we've got the boundary condition at A and the boundary condition at B. And also remember that the Sturm-Liouville problem is defined to be regular if and only if the interval is finite, so A and B are finite numbers, and also that P is non-vanishing on X. Okay, so we just talked about the spectral theorem and saw that the self-adjointness of the Sturm-Liouville operator is going to guarantee for us an orthonormal basis because of the spectral theorem. However, more is true in the case of Sturm-Liouville. So they're not just self-adjoint, they also have other nice properties. And so in particular, the eigenvalues form, well, first off, it's possible in infinite dimensions to have spectrum which is continuously distributed. So instead of having eigenvalues appear as discrete numbers with corresponding separate eigenfunctions, it's possible for them to be kind of smeared out in a continuous way that I don't really want to get into. But for Sturm-Liouville, it turns out that the only spectrum you get is discrete. So you get this nice sequence of numbers, and they are all separated from each other. They don't clump up. And they form an increasing sequence that tends off to infinity. So all the eigenvalues are distinct also. You don't have higher multiplicity. So since you always have multiplicity 1 for every eigenvalue, this means also that you have exactly one eigenvector or one-dimensional eigenspace for each eigenvalue. So this means, one up to linear independence eigenvector per eigenvalue. And also, and this is sort of interesting and strange, but you've seen this in the examples we looked at, the eigenfunction un, so the eigenfunction corresponding to the nth eigenvalue as listed in this order, will have exactly n minus 1 zeros in the interior of the interval. And so if you remember back to our very first example, something like the Dirichlet boundary conditions, the eigenfunctions that we had for that one are, the first one is the sine. So that one has 0 zeros in the interior, right? But then when we go up to the next one, we have 1 0, and then when we have the next one, we have 2 zeros in the interior, and so forth. And then the other example that we saw, where we had functions that looked like this one, and then this one with 1 0, and then this one with 2 zeros, and so forth. So that kind of pattern always happens, even with cases where the solutions are polynomial functions and not sines or cosines. And so we'll see some examples of that probably later on. So let's see. So I'm not going to prove this whole thing, but I will do a little proof of the fact that the multiplicity of a given oh, sorry, that's the wrong one to write. I want to show that the dimension of the eigenvalue is equal to 1. Okay, so suppose we've got LV1 is equal to lambda V1, and that LV2 is equal to lambda V2. Okay, so then I want to show that V2 and V1 are parallel. In other words, that one is a scalar multiple of the other. Okay, so what can I do? Well, 0 is, let's see, so here we're going to have V2 lambda V1 minus V1 lambda V2, so I'm setting something up for an inner product. And so this is, well, actually not quite an inner product. This is V2 L V1 minus V1 L V2, in virtue of the fact that these are both eigenvectors for eigenvalue lambda. And then if you remember having seen this expression before, I showed it to you in a corollary where I called it Lagrange's identity. And so Lagrange's identity tells you that this is the derivative of p times the Wronskian. And so here, this is the Wronskian of V1 and V2. So that, the 2 by 2 determinant with those entries. And so now what we have is that so this tells us that since the derivative of PW is 0, we know that PW has to be a constant. And so what is that constant? Well, if we look back at the boundary conditions, we see that the Wronskian at A is equal to 0, and also the Wronskian at B is equal to 0. So that tells us then that C is equal to 0. And now what we have is that PW is equal to 0, but P is required to be non-zero. So now we know that W is equal to 0. But the Wronskian can only vanish if the functions are dependent by stuff you learned in a previous ODE class. So, or actually the author, Logan, talks about this briefly in the chapter in the book. He does a cute little way to see how it's true for the 2 by 2 case. When the Wronskian is 0, it means that the set is dependent.